We're going to talk about permutations in this lesson. We're at 15.1b, which tells us there's a 15.1a. So if you get lost or confused, my advice is to go back and watch 15.1a. It's linked in the description. A permutation of a set is an ordered arrangement of that set without repetition. We can find the total number of permutations of a set of n objects. We can use the fundamental counting principle to determine the number of ways that n objects can be arranged in a certain order. We would do n sub 1 times n sub 2 times n sub 3 and so on to n sub k. Then we'll have a permutation of the objects. So permute means to change the order or arrangement of. It means to arrange in all possible ways. If we have a set of 3 objects, let's say they're A, B, and C, how many different ways can we arrange them? We can pick any of them to be first, so there's 3 choices for the first object, A, B, or C. This leaves 2 choices for the second object because we can't repeat, remember, without repetition. So if we do choose A first, our second spot can either be a B or a C. If we choose B first, we can have an A or a C in the second place. If we choose C first, then we can have an A or a B, see? And the third object is the only one remaining. If we choose A first and B second, our only choice for the third spot would be a C. It's the only one left. If we choose A first and then C, B is our only choice, see? And by the fundamental counting principle, there are 3 times 2 times 1 possible arrangements. Here's the arrangements. We have 6 permutations of 3 elements. A, B, and C are the elements, see? And we have 6 permutations. Remember, these are elements of a set. They're members of a set, okay? We can generalize this to a set of n objects. We have n choices for the first selection. Then we have n minus 1 for the second selection. So it's minus 1 because we already made the first choice. We have 1 less choice, don't we? We have n minus 2 for the third, and so on. So for the nth selection, there's only going to be 1 choice, the one that's left over, that hasn't been used yet. And the number of permutations of a set of n objects taken n at a time is symbolized as npn. You might even see it with the n floating up here. Some teachers write it that way. And it's read as n permute n, or we could say npn. So I have a theorem for you. The total number of permutations of a set of n objects is given by npn is equal to n times n minus 1 times n minus 2, n minus 3, and so on. 3 times 2 times 1. So here we have 4 different colored gems of a pink, purple, blue, and green. How many different ways can these gems be arranged in a line? So there are 4 choices for the first position. Pink first, purple first, blue first, or green first. So here I've got them arranged with the pink first. Here's with the purple first. Here's with the blue first. Here's with the green first. Okay? So if we choose pink first, there's 3 remaining color choices for each second position. If pink is first, it's already used. We can't repeat. So now we have purple, blue, or green that can be in the second spot. If we do choose pink and then purple, we only have 2 choices for the third position, blue or green. And if we do choose blue, we only have 1 choice, the green one, see? And it's the same for each one of these. And by the fundamental counting principle, there's 4 times 3 times 2 times 1 possible choices, which is 24 possible choices. So we have 24 permutations of 4 elements. And the 4 elements are the 4 colors, see? We can find 1p1. How many ways can we arrange a 1? 1. We can find 4p4. We do 4 times 3 times 2 times 1. It's going to give us 24, like the gems. We can find 8p8. We do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We do all that multiplication. We get 40,320. Here's another example. So a mother cat has 6 kittens, and they each had a different coat. There was a black, white, gray, orange tabby, calico, and tortoise shell. How many possible birth orders are there? Were they born in the order that I wrote them, or what other orders could there have been? There's 6 kittens, so we do 6 times 5 times 4 times 3 times 2 times 1. That tells us there's 720 different possible birth orders for these kittens. We don't know what those permutations are. We don't know what the exact orders are written down, but we know how many there are. And permuting is much quicker than making a list to find how many birth orders are possible. If it's a small amount, like just 2 or 3 things, it's possible to make the list, but sometimes you end up with a long list, and it's easier to just do the permutations. See? So here's some other examples of permutations. What if somebody's ATM code is a 4-digit number, and you know the numbers are a 2, a 3, a 4, and a 5, but you don't know what order they are in? We could write the different ways that they could be entered, couldn't we? Because there's 4 numbers, we would do 4 times 3 times 2 times 1, so there'll be 24 different possible ways of putting these numbers in to get the right ATM code. If someone said their locker combination was a 5, an 8, and a 12, but not necessarily in that order, how many tries would you have to do before you got the right combination? Well, there's 3 of them here, so we do 3 times 2 times 1. There's 6 different possible ways to enter this to get the right order, see? A permutation applies if order is important. Here we've got these puppies in a container. How many ways can we arrange the order of these puppies to take their picture? We could put the brown one in the middle or over here and put the black-eared one up in front. Well, there's 3 puppies. We do 3 times 2 times 1. So there's 6 different ways to arrange these puppies to take their picture. Okay? Our next lesson is factorial notation. It's going to be 5.1c. So if you've never seen an exclamation point in math, you will now. So this is n factorial. That's how you read the exclamation point, as factorial. Okay? If this video helped you in any way, hit the like button so I know. And if you get lost or confused, remember you can always go back and hit the description to watch the previous videos, okay? I hope you have a great day, and I'll see you next time. Bye.